Today we have a very beautifully geometric topic. These surfaces occur in lots of neat applications, and they have cross sections actually that are conic sections, and so they play into some things we've already done. These are called the quadric surfaces. These are the standard 6 non-degenerate quadric surfaces. The first one is an ellipsoid. It's got that name probably partly because its cross sections are all ellipses. And look, its equation is just about like an ellipse. X squared over a squared plus y squared over b squared plus z squared over c squared equals 1 is the equation of an ellipse in the plane, that plane curve, just with one more term. The ellipse equation gives you a curve in the plane. The ellipsoid equation gives you this surface in 3 dimensions. Now these are kind of easy to remember because they are similar to conic section equations, and they're similar to each other too. Here's the next one. A hyperbola of one sheet is this kind of almost like a spool shape. X squared over a squared plus y squared over b squared minus z squared over c squared equals 1. So you just take this plus from the ellipsoid to a minus, and you get a hyperbola of one sheet that looks like this. We'll figure out shortly how to draw these things. Now if you change 2 of these pluses to a minus, you got z squared over c squared here, minus the x squared over a squared minus the y squared over b squared terms equals 1. Then you've got this hyperboloid of 2 sheets. Comes in 2 pieces like that. Next you've got the elliptic cone. It's got elliptical cross sections this way, but it's a cone, so it's like an hourglass with elliptical cross sections. Z squared equals x squared over a squared plus y squared over b squared. Here's an elliptic paraboloid. Z equals x squared over a squared plus y squared over b squared. See how similar it is? Z squared here changes to z here. This one is almost like this, except there's not a 1 on the right-hand side, right? And you got rid of the c squared. Instead you've got 0 left over. And here is the hyperbolic paraboloid. Z equals x squared over a squared minus y squared over b squared. Change that plus to a minus, so their equations are very similar. And their names sound kind of like conic sections because of their cross sections being like conic sections. There we go. I was trying to get my page back here. Here's the Wikipedia page showing the same thing. There's the ellipsoid with the same equation. Here's the elliptic paraboloid, hyperbolic paraboloid, hyperboloid of one sheet. I'll call it an elliptic hyperboloid of one sheet. So the names are just about the same. Here's the elliptic hyperboloid of 2 sheets. The elliptic cone. They wrote their elliptic cone equation a little differently, you notice, but it's the equivalent set of points. Here's some other things that are the non-standard cases that you can get from some equations we're coming up with. There's 6 non-degenerate quadric surfaces that we have. Now, an interesting thing about these is that they all are highly related to equations that we tend to see in practice. You remember that the conic sections, every conic section could be written in the plane as a particular form: ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Every equation of this form was either a conic section, a degenerate case, or had no solution. The degenerate cases were like lines, and a pair of intersecting lines, a point. So this encompasses basically polynomials through second order equals 0. So they're very common kinds of equations. You just have this kind of equation, and then you can do a rotation in the plane to get rid of this term here, remember, and then it becomes a conic section in standard form by completing the square. We can do a completely analogous thing now with quadric surfaces. It turns out that every quadric surface can be written in this form in 3 dimensions. Ax squared plus bxy plus cy squared. It starts out the same, but now we've got 3 variables, so there's a plus dyz plus ez squared plus fxt plus gx plus hy plus iz plus k equals 0. Every equation of this form, which is up to second degree polynomial in x, y, and z, equals 0. This very important equation is a quadratic surface, a degenerate case, such as one of those cylinders you saw, or a plane, or something like that, or it can have no solution. And just like in the conic sections, you can do rotations, this time in all 3 coordinate planes, and put it into this standard form, and by completing the square, get one of those standard forms we see for the quadratic surface. We're not going to do this because rotations in 3 dimensions takes too much time, but if you take a linear algebra class or something like that, you can see rotations and try this out. It's the same concept. So now we want to try some problems with that, and see if we can recognize how to sketch some of these quadratic surfaces. Oops, got the wrong one up. So here's some book problems. Suppose I write down the equation z equals x squared over 4 plus y squared over 9. What could that be? Well, what you can do is look at the cross-sections parallel to the coordinate planes. Now, cross-sections intersect these curves called traces. And so let's draw a few traces, and maybe we can figure out what the picture looks like. So we have to sketch z equals x squared over 4 plus y squared over 9. If we didn't know those shapes we saw in the book, how could we figure out how to do this? We can make traces like this. We could set z equal a constant. Z equal a constant 1 makes a trace. The intersection of this with the plane z equals 1 is 1 equal x squared over 4 plus y squared over 9. Well, what is that? We recognize that as the standard equation for an ellipse. And we can try some other cross sections parallel to the xy plane. We can take 4 equals x squared over 4 plus y squared over 9. What's that? Well, we can equivalently divide that by 4 and get 1 equals x squared over 16 plus y squared over 36. This ellipse had semi-axes of 2 and 3, right? This is x squared over a squared plus y squared over b squared. A and b are 4 and 3. I guess I should call it a 3 and b 2. Sorry, 3 and 2. And then over here, a is 6 and b is 4. And so we start drawing these cross sections like this. Here's the in the z equals 1 plane, 1 unit above the xy plane. We draw this ellipse. Center at the origin, semi-axis 3 in the y direction and 2 in the x direction. So within this plane, we go over this way 1, 2, 3 units, and over out this way 1, 2 units, and we draw this ellipse is the intersection of this surface with the plane z equals 1. Now we go up to the plane z equals 4 here. And on the z equals 4 plane, we draw an ellipse with semi-axes 6 and 4. And so it's a bigger ellipse like this. If we were to do the z equals 0 trace, we get 0 equals x squared over 4 plus y squared over 9. Well, non-negative term, non-negative term, the only solution is x equals y equals 0. We get this point. And we put a negative here, we get no solution. If you do enough of these, you'll start to see a figure coming out that would, if I draw them correctly, that when you put it together, it looks kind of like this. It is actually an elliptic paraboloid. But you see these elliptic cross sections. Now we can do traces in the other direction. Suppose I do, for instance, the equals 0 trace. By putting x equals 0 in the equation, I get z squared equals y squared over 9. Actually, z equals y squared over 9. That's a parabola. Alright, the basic parabola upward. And so in the yz plane of the board, I draw this parabola. There's the yz plane of the board, x equals 0. And here's the parabola. Now I can start to see this coming out. It's a dish with elliptic cross sections this way and parallelic cross sections this way. Similarly, I can draw x equals 1 and get another parabola up here and sketch it and so forth. I can also draw the y equals 0 trace in the xz plane. It's this one right here, right? Here's the z and x axis in this plane. What do I get? If I put y equals 0, I get z equals x squared over 4. Here's another parabola, and I get a parabola that looks like this. So there it is. Here's how we usually draw the elliptic parabola. We draw, it goes up forever, as you can see from the equation, but we draw an ellipse up here, and we draw a parabola down here. And if we want, we draw a few more lines in here to sort of give it some body. But there's an elliptic paraboloid, and its name gives away what the cross sections are. All right, so that's that one. Let's try this one. Suppose I wanted to sketch x squared over 4 squared minus z squared minus y squared equals 1. What in the world could that be? Well, you remember, if you take the ellipsoid and put in 2 minuses and still have 1 on the right, you have a hyperboloid of 2 sheets. Rewrite this in this usual form of x squared over 4 squared minus z squared over 1 squared minus y squared over 1 squared equals 1. To see that it's exactly the hyperboloid of 2 sheets, except in the hyperboloid of 2 sheets, z was here and the x and y terms were subtracted. So what does that mean? It means we've interchanged the z and x axes in that picture, and the hyperboloid of 2 sheets, instead of opening up like this, is going to open about the x-axis, about the positive terms variable. So it's going to actually come out of the board like this, based on our intuition from that picture. But just like in the last example, we can sketch it by doing traces. Let's put for instance, the z equals 0 trace, right? If I put z equals 0 in this equation, let's just put it up here actually. X squared over 4 squared minus y squared over 1 squared equals 1. That's a hyperbola with a equals 4 and b equals 1. So we have a hyperbolic cross section in the xy plane. So in this z equals 0 xy plane, I sketch a hyperbola down here and a hyperbola down here. And our experience with hyperbolas tells us how to plot a few points. For instance, when y equals 0, we get x equals 4, right? So this is the point, 4, 0, 0. And similarly, x can be minus 4, and you get the point minus 4, 0, 0. So we're well on our way if we memorize the different quadric surface pictures, and we say, oh, this is just the picture rotated so it opens about the x-axis, x coming out of the board, y over here, and z up here for standard orientation. Now we've got this cross section, this one. Now we can do some other traces. If we put, for instance, the x equals 0 trace, the yz plane of the board, right? Now I can see that if x equals 0, there's no solution. Minus z squared minus y squared equals 1. Non-positive equals positive. There's no solution. Well, that's kind of what we expected. We have a sheet out here and a sheet out here. But if we make it a little bigger, if we make it x equals 4, then we get 1 minus all this stuff equals 1. And y and z both have to be 0. We get these 2 points. And if we so we get the point 4, 0, 0, minus 4, 0, 0 by putting x equals 4 in here. This becomes 1 and cancels the 1. You get minus z squared minus y squared equals 0. Now we can put z 64 over 16 is 4 equals 4 minus z squared minus y squared equals 1, which says z squared minus y squared equals 3. That is z squared plus y squared. And you divide that through by 3, and you finally get an ellipse of seeming axis square root 3. And so, in this plane out here, x equals 8, we get an elliptical cross-section. Actually, in this case, a circular cross-section, right, of radius square root 3. So in this case, the elliptic, the hyperboloid of two sheets it generally has elliptic cross-sections. In this case, it'll have circular cross-sections. So we start to draw that, hyperbolas in the xy plane, and then circles out here, and we get a picture sort of like this. I'm going to get a lighter colored chalk here. Let's try this one more time. These are hard to draw. Like that. And like that. A sheet coming out this way and a sheet going out that way with elliptical cross-sections parallel to the YZ plane and hyperbolic cross-sections in this direction. So that's how you can draw a lot of these. And amazingly, these things come up in lots of scientific applications also, and in natural phenomena. Here, for instance, is a little thing I made with some stretchy string. This is connected between two peanut jar lids, and here's a little dowling in the middle. And if you twist this thing just a little, look, you made a hyperboloid of one sheet, and kind of a neat result occurs from that you can see down at the museum. The museum will put a board up with a curve in it that's a hyperbola. And then they'll put a straight bar out here, kind of at an angle at the end of another bar, and it stands on this podium. And this bar rotates around this bar, and you're going to force this straight line through this curve. How do you do it? Well, as it swings around, this is actually a hyperbola, and it's like the stretchy string. These straight lines actually, as they turn around in the shape of ellipse, because the cross sections of a hyperboloid of one sheet are hyperbolas and ellipses, and you can prove it just by taking traces like we did with the other two figures. So let's try a couple of these other ones. Suppose, for instance, I said, let's sketch this one, z equals y squared minus x squared. What should that look like? Well, when you recognize it's a second degree polynomial in 3 variables, this is a quadric surface or degenerate case or no solution. So if I want to sketch z equals y squared minus x squared and sketch it, if I try taking traces, I can put z equals 1 and get 1 equals y squared minus x squared, a hyperbola, right? With a and b equal to 1. If I put z equals 0, I get y squared minus x squared equals 0. Equivalently, x squared equals y squared. Equivalently, 2 lines, y equals plus or minus x. And so what you get in the traces parallel to the xy plane are in general hyperbolas. You can try some other numbers here, But in the xy plane itself, you get a pair of intersecting lines. So you generally get things like this. Here's maybe the z equals 1 plane. Sitting up over the xy plane, 1 unit. Here's your hyperbola, 2 branches. But down here you get intersecting lines. And if you take traces in the other directions, for instance, if I put in this equation y equals 1 and take that trace, I get z equals minus x squared is a parabola. And if I put the, let's say, x equals 1 trace, or x equals some other number, I'll get z equals y squared minus a number, which is a parabola upward. So parabolas downward in the xz plane, or parallel to the xz plane. Parabolas upward, parallel to the yz plane. This is the hardest one to draw, is why this one really needs an example. When you put this all together, this is actually what you get. This parabola is down in this direction, like this might be in the y equals 1 plane right here. We get a parabola downward, z equals 1 minus x squared. And then we get something like this, hyperbolas, parabolas, and this comes down like this, and it's a saddle shape. So the hyperbolic paraboloid has hyperbolas and parabolas. This is the hardest one, I think. Oklahomans, I say, can draw it because it's a saddle, right? But it still takes a little work. Hyperbolic paraboloid, its cross sections are hyperbolas and parabolas. And the idea is that if you put the z term not squared equal to the other ones, then this is a saddle that you sit down on the origin. And you can tell which direction it goes by which direction the parabolas are down. Here's a parabola up in this direction. This would be like the yz plane. If you put x equals 0, this could be the parabola z equals y squared here. And you get parabolas downward in this direction, and you get hyperbolas in this direction. So there's how to sketch a hyperbolic paraboloid, the hardest one. All right, now the next hardest problem. Sometimes you're given one of these quadratic surfaces not in its standard form. I won't put in the cross terms here, the xy, the yz, and the xz terms. Again, you can get rid of those with rotations when you do a little more linear algebra or something. Suppose we've gotten rid of the cross terms with rotation. How can we sketch what quadratic surfaces is, or determine that it's a degenerate case, right? Well, we complete the square. So what you do is you collect all the x terms with the coefficient of x squared factored out. You write that as 9x squared minus 2 gives you 9x squared minus 18x. Then you collect all the y terms together with the lead coefficient of y squared pull out. 1 times y squared plus 2y, this is in 2x. And then the z terms with the coefficient of z squared pulled out. 4z squared plus 4z, all equals 10. And now you complete the square in each of these. What do I have to add in here to make this a square? I take 1/2 of this number, is -1, and square it. I get 1, so I need 1 in here to make this a perfect square. This is 9 times x squared minus 2x plus 1. Well, I can't just add 1 over here. I have to balance the equation by adding 1 on the right-hand side. And then also in here, I've got 1 times y squared plus 2y. What do I have to add in here to make a square? I take 1/2 of this number. 1/2 of 2 squared is also 1, so I need plus 1 in here. Oh, and I forgot, I messed this up. This is 9 times 1 I added here. I needed to add 9 last time. And then here I added 1 times 1. I need to add 1 more to each side to balance it. And then here I've got 4 times z squared plus 4z plus what makes a square? Well, I take 1/2 of 4 is 2 and square it, and I get 4 I need to put 4 in here to make a perfect square. 4 times 4 is 16. I've added to this side. I balance it with 16 on the other side. Now I have 9 times, this is x minus 1 squared, plus 1 times, this is y plus 1 squared, plus 4 times, this is z plus 2 squared, equals 19, 35, 36. What does that look like? Well, if you divide it by 36 to make 1 on the right, you can write this as x minus 1 squared over 4 plus y plus 1 squared over 36 plus z plus 2 squared over 9 equals 1. Or finally, x minus 1 squared over 2 squared plus y minus a negative 1 squared over 6 squared plus z minus a negative 2 squared over 3 squared equals 1, whereby we recognize an ellipsoid, except x has been replaced by x minus 1 and y by y minus a minus 1 and z by z minus 2. Remember, in any equation where you replace the variables by the variables minus some number, that's just a translation. Takes the exact figure and slides it rigidly. So this is an ellipsoid with semi-axes 2, 6, and 3, but centered at 1, minus 1, minus 2, 1, minus 1, minus 2, the numbers that are subtracted. So we go out to this far corner of the box at 1, minus 1, minus 2, the numbers that are subtracted in there, and we draw an ellipsoid with semi-axes 2 in the x direction coming out this way, 6 in the y direction, 1, 2, 3, 4, 5, 6, and 3 in the z direction, 1, 2, 3, and you have cross sections about like this. There's sort of an equator for it in that direction, and like this. And here's our ellipsoid. Looks about like that. It's got elliptical cross sections in all 3 directions. If you try setting x equal a term, you say the rest is an ellipse. For instance, set x equal a constant, take the trace, you get an ellipse for the rest of the part. Set y equal a constant, you get an ellipse. This will have elliptical cross sections in all 3 directions. This is an ellipse in this direction, an ellipse in this direction, an ellipse in this direction. So there's the sketch of the ellipsoid. I'd like you to be able to sketch those. Finally, I'd like you to be able to do some related equations. If you get an equation like this is not one of your standard forms for a quadratic surface. But by squaring both sides, you can figure out how to sketch it nonetheless. If you square both sides, you get z squared equals x squared plus y minus 1 squared. That looks a lot like something we've seen, except that y was replaced by y minus 1. This is an equation for the elliptic cone, and actually in this case, the right circular cone, just like an hourglass, because these two numbers are equal. In general, the elliptic cone is z squared equals x squared over a squared plus y squared over b squared when the vertex of the cone is at the origin. By replacing y by y minus 1, I have shifted it out 1 along the y-axis, so it's right here, 0, 1, 0, and what you'll get is cross sections up here that in general are ellipses, but in this case, if you try the traces, like put the z equals 1 trace, you get 1 equals x squared plus y minus 1 squared. You observe you get a unit circle, not an ellipse. So the elliptical cross sections that you usually get are degenerated into circles in this case. And what you have is an hourglass shape like this. In the plane, z equals 1, the cross section is the unit circle straight over the point 0, 1, 0. And so we have this kind of a picture. Circular cross sections going up actually a half a cone, because what happened when we squared both sides was we introduced new solutions. I wrote implied because this implies this, but it's not equivalent. Now z could be, this has 2 solutions, z equals plus or minus this square root. The radical means the non-negative number that has this square, so we only allow non-negative z. So these will be equivalent if I add the stipulation that z has to be greater than or equal to 0. So what we have is half the elliptic cone the half or the z coordinates are not negative. This big funnel, if you like. And there's how to draw that one. Try the homework problems now. I think that'll give you a good idea how to do them.